Hello friends, my name is Jimit and welcome back to the Civil Technology channel. So in this video, we discuss about how we can design the singly reinforced rectangular beam based upon the IS 456 codal provision. So many of the viewers and students earlier comment me, sir, can you teach the civil engineering related subject, especially the RCC design and all. So here I am starting from those types of video. So please watch till the end and comment me if you really like, if you really want these types of more videos. So I will make for you guys. So let's start it. So what I am doing here, I am taking one problem related to the beam design, and in between we can discuss the various parameters related to the beam design as well as the codal provision related to the beam design. So let's start. So problem statement is a rectangular beam which is simply supported on both of its ends. The support width is 230 mm. Means whatever the column or walls on which this beam is supported, whose width is 230 mm. Clear span of the beam is 6 meter. Means whatever the clear span, clear length we can see inside the room, that is the 6 meter length. Width of beam is already given in the problem, that is 300 mm. So we do not have to calculate that again. Characteristic superimposed load. You people may aware about the live load, which is very much similar to the imposed load, and whose value is given as 12 kN per meter. So actually this we decide based upon the occupancy and some other loads, but here we discuss about the beam design. So first time, so I am little bit makes the problem easier. So in next video we can see more complicated problems also. Okay, let's see first simple problem. Characteristic strength of concrete, that is 20 Newton per mm square. Means M20 grade concrete here we use, and if we talk about the steel grade, and that is the 415 Fe 415 we can use for the beam design. So this is the given data. Please note down in a copy. So further calculation you can correlate the things very easily. If you see the diagrammatically, then these types of beam, it's look like this is our beam. This both yellow is supports, that is a column or wall depending upon your plan and all that things. Okay, this is our clear span, that is 6000 mm, 6 meter, and this is our width of the support, that is 230 mm. Okay, so this is our problem. Now our job is to design this rectangular beam. Means how much top reinforcement come, how much bottom reinforcement come, and how much the shear reinforcement coming from this beam. So first step is to decide the depth of the beam. So for rectangular beam, this is the thumb rule, that is depth of beam will be equal to 1/12 to the 1/15 of the span. Means whatever the clear span we have, most 1/12 or 1/5 in between, our depth of beam will be vary. Okay, so this is a general thumb rule. It is not compulsory the depth of beam value lies in between these, but normally it lies in between these for a rectangular beam designs. Okay, so based upon that, if we calculate the depth of beam, then it is the 1/12 of the 6000 to 1/15 of the 6000. Means our depth come in between 500 to 400 mm. So this is our actually effective depth. What is effective depth? On that we can discuss in some other video. Please comment me if you really want about that, so we can discuss in detail that video. So let's consider the 400 mm depth of the beam. Okay, so next if we revise, next if we require, we can revise the depth. Okay, but as of now let's take the 400 mm depth and consider the overall depth 450 mm, means we considering the 50 mm cover along with this effective depth. So total depth of beam coming out is 450 mm. Okay. So how we calculate the clear cover and all that things is very much interesting and topic we can discuss in some other video, because if we can discuss in this video, then this video will be very much longer and boring also. So let's forget about things right now. Okay, so this is our first step, decide the depth of the beam. Next is let's decide the effective length of the beam. Means effective length means whatever the clear span you have, as well as we have to consider the some extra length like width of support length or effective depth length based upon the different criteria. Okay, if you read the IS 456 code, then you can find for rectangular beam these are the condition for the effective span, that is clear span plus width of support on both the side, or clear span plus effective depth of the beam. So this is the criteria. These are the two conditions. Based upon that we can decide the effective span of the rectangular beam. Similarly, if your beam is something else, means your beam is continuous type or cantilever type, then this condition will vary. So accordingly you will take the formula for the effective span calculation. So here is our rectangular beam. So for rectangular beam these are the two conditions, and whatever the lesser value comes from both of this condition, that will be taken as the effective span of our beam. So let's calculate. So clear span, as we here see, is 6 meter already given in the problem, and width of support is 230 mm. So what we people do, we can take the half of the width of support from both the side. Okay, from our problem both the side width of support value is same, that is 230 mm. But in actual problem, in reality, there are many times this happen, our both the side support width will be different. So in that case we have to take half of both the side, and so I am here representing the width of support in this way, half of from left side and half from the right side. So this is our first condition. Second is clear span plus effective depth. Effective depth just we calculated 400 mm, so 6 plus 0.4. Based upon this, if we calculate, then the value come is 6.23 meter and 6.4 meter. So what we do, minimum of this we can consider for our effective span of the beam. So in our problem the effective span comes 6.23 meter. So whatever the value you here seen in a bolted color, so that please note down in a copy. Also I am considering that value here, so you can easily go relate the next steps. Okay, so this is our first two step, depth of beam and effective span, very much important for the calculations. Okay, so if we look diagrammatically, so this way it looks. This is our effective depth, that is whatever your first bar come at the bottom of the beam, from there, from its center to the top of the beam, that is our effective depth of the beam. And if we talk about effective span, then it's center to center distance mostly from the width of support from both the side plus clear span of the beam, that is our effective span of the beam. Next step, we can design the reinforcement of our rectangular beam. So we can design the beam in moment condition. So for that we have to calculate the moments, and for moments we have to calculate the loads which coming to the rectangular beam. Okay. So first we calculate the self weight of our beam. So self weight formula is width of beam multiplied by overall depth of beam multiplied by density of beam, and one is the per meter. We calculate the per meter length of loads. Okay, so means we calculate all the loads in UDL form. So for that purpose I taken as a length 1 meter. So all the data already given, that is width of the beam already given 300 mm, so 0.3. Overall depth we just calculated 450 mm, so 0.45. Density of concrete we consider as 25 kilonewton per meter cube. So in that way this 25 comes and per meter length. So this way self weight of our beam comes 3.375 kilonewton per meter. So this is our first load. You can say this is our dead load of our beam. Next load coming is the live load, that is imposed load, that already given in problem, that is 12 kilonewton per meter. So based upon that we can calculate the design load. So design load formula is 1.5 times dead load plus live load. So this is 1.5 is the factor which if you read the IS 456 code you can easily understand how this factor coming out. But if you want on more information regarding this, you can comment me. I will give more information in for videos or comment box. So dead load, that is the self weight, just we calculated 3.375, and live load is the 12 kilonewton per meter already given. So based upon that our design load come 23.06 kilonewton per meter. So using this load we can calculate the moment. As our rectangular beam is simply supported, so you may aware the bending moment formula for simply supported beam is WL square by 8. So just that formula we use for the design moment. So W, that is our design load, and L is our effective span of the beam. So all the values already we calculated. So based upon that 1 by 8 multiplied by W 23.06 multiplied by 6.23 square, that is our effective span. So design moment comes 111.87 kilonewton meter. So whatever the reinforcement we have to calculate is based upon this value of the moment. But before that we have to check whether our beam is really a singly reinforced beam or doubly reinforced beam, because if it is doubly reinforced then the moment calculations are furthermore modified, and based upon that we can calculate the area of the reinforcement. Okay, so before that we calculate another parameter, that is the design shear. So for simply supported beam we already know the formula, that is WL by 2 for the shear. So for design shear just we use that formula and calculate the design shear for our problem, and its value coming out is 71.83 kilonewton. So these are the design values, these are the values. Based upon that we can calculate the reinforcement required for our beam. So please note down this moment value and this shear force value. So now we check whether our beam is really singly reinforced or doubly reinforced. So how we check? For that we have to calculate one parameter, that is called as a XU limit. So XU limit formula is 0.48 times the D. So how this comes? So if you read the IS 456, there are one table in that is specify whatever your characteristic strength or whatever your grade of steel, based upon that XU limit by D value will vary. So if you use the 250 mm grade steel, then its value coming out 0.53. If you use 415, then it's come for 0.48, and for 500 steel it coming out 0.46. So in problem we can see we use the Fe415 grade of the steel. So based upon that XU limit by D value coming out 0.48. So we require XU limit, so just 0.48 multiplied by D, that is our effective depth of the beam, and the value coming out is 192 mm. So based upon that we calculate what is the maximum moment that our beam can carry using this size and all other parameters. So for that we have one formula, please note down. MU limit, that is maximum moment that will handle by this beam, is 0.36 multiplied by FCK, that is grade of concrete, multiplied by width of the beam, multiplied by XU limit, multiplied by D minus 0.42 of XU limit. So all the values we already calculated, just put down in the formula, that is 0.36 multiplied by 20 grade of the concrete. Here you can see width of the beam 300 mm already, here no, sorry, here is the beam. XU limit just calculated 192 mm. Effective span we calculated 400 mm, okay, and 0.42 times the 192. So if you calculate on your calculator, you can get the value 132.45 multiplied by 10⁶ Newton mm. So this value comes in the Newton mm, but our moment we calculated earlier in a kilonewton meter unit. So we have to convert this into the kilonewton meter units. So if you calculate, then here the value comes is 132.45 kilonewton meter. So this is our maximum moment that will carry by this rectangular beam very safely. So if our moment is more than this value, then our beam is not a singly reinforced beam. It is a doubly reinforced beam obviously, and or something else also. So but in our case the MU value will be less than the MU limit value, right? So here you can see MU limit is greater than MU. So based upon that we can conclude that our section is singly reinforced section, means our beam section we can design as a singly reinforced beam section. Okay, so likewise we can decide whether our beam is singly reinforced or a doubly reinforced beam. Okay, so now we calculate the required area for our beam. For that we have a formula. This is the formula, MU limit or MU. Okay, whatever the design moment we consider, okay, that value we can here taken. Okay, it may be MU limit or it may be MU, depends on the value of your moment. So MU will be equal to 0.87 into Fy into AST. AST is our area of reinforcement in a tension side, multiplied by D effective depth multiplied by 1 minus AST into Fy upon BD FCK. So this is the formula. Based upon that we can calculate the AST value. So all other parameters we already know except the AST. So just put down all the parameters value. So for our design moment is 111.87. So in our case this is not a MU limit, this is the MU, because MU is already less than and our section is singly reinforced. So we can take on as a MU value here. So note down here all the parameters we can take on in a unit Newton mm. So here I multiply the moment with the 10⁶ factor, and based upon that we can calculate the AST value. So AST value comes is 921.4 mm square. So this much area of reinforcement is required for our rectangular beam of this size. So if we use the 20 mm dia bar and 3 numbers of 20 mm dia bars, then its area comes very much near to this required area, that is 942 mm square. So we use the 3 bars of 20 mm dia for our beams in a tension side, that is the bottom reinforcement. So this way we can design the bottom steel for our rectangular simply supported beam. Next we have to design the shear reinforcement. For that we have to first of all check whether shear reinforcement we have to design or whatever the minimum reinforcement code suggests us, that is sufficient already. Okay, so first we have to check that things, and based upon that we can go further. So design in shear. For design in shear, first of all let's calculate few parameters, like first is tau v. So tau v, the formula is tau v is Vu upon Bd. So if you see the IS 456 code, you can get all this formula in that code very easily. Just take those formula and related parameter calculate, so you can easily calculate those parameters. Okay, so for tau v we require Vu, that is our design shear force, that already we calculated 71.83 kilonewton, and B and D are the width and the effective depth of the beam, that we already know. So just put down the values, and here also please note down the unit we consider Newton and mm. So based upon that our shear force value will be multiplied by the 1000, and tau v value comes out at 0.598 Newton per mm square. So this is a tau v value. Okay, means design shear stress. Okay, next we have to calculate the percentage of steel. Why? Because for tau c calculations, we require the percentage of steel. So for percentage of steel, the formula is AST provided, means whatever the reinforcement we provided, like we provided the 3 bars of 20 mm dia. So what reinforcement coming out is 942 mm square. So that we use for our percentage of steel calculations, and based upon that we calculate the percentage of steel, and that is 0.785. So using this value we have to calculate the tau c value. So for that we have to use one table which is already given in IS 456. Table number 19 you can see design shear strength of the concrete. Okay, so for that we require grade of concrete and percentage of steel parameter. Okay, so we already calculate the percentage of steel, that is 0.785. so here what you have to do, you have to interpolate the two values, because for 0.785 IS code doesn't give the exact value, it gives the 0.25 and 0.5, 0.75, 1.1, 1.25 likewise. So what you have to do, just here take two values, one upper side and one lower side, that is for our case 0.785. we have to consider the here 1 and 1.25 value. Okay, and our grade of concrete is M25. So just here see in the M20 column, and for M21 you have a 0.62, and for 1.25 you have a value 0.67. So if you interpolate these two values, you can get the value, that is 0.57 Newton per mm square. Sorry, our value actually lies between 0.75 to 1. So the value coming out in between the 0.56 and 0.62. So based upon that our value come 0.57 Newton per mm square. Next parameter, we have to calculate the Proxy Max. So for Proxy Max also we have to consider another table which is given in IS 456. So maximum shear stress Proxy Max for M20 grade concrete is 2.8. So this way we calculate the Proxy Max value simply 2.8 Newton per mm square. Now what we have to do, we have to compare all the three values, means tau v, tau c and Proxy Max, and based upon that we can identify where our sections lies and what the next step for the design of shear, because in every condition the steps are different. For our condition, what are the steps? Let's see. So let's see first the conditions and the meaning of those conditions. So first condition is tau v is less than tau c is less than Proxy Max, means Proxy Max value is greater than both of these values, tau v and tau c. So if our conditions lie between this condition, then it means we do not require any further calculations for the shear reinforcement, means whatever the minimum shear reinforcement suggested by IS code, that is very much sufficient for our beam. So let's see whether our case lies for this condition or not. So for our case, tau v value is 0.598, tau c value is 0.57, so which means tau v here greater than tau c. So our case, this condition not apply, so just forget, means we have to calculate the shear reinforcement for our problem. Now let's see whether we have to calculate directly shear reinforcement or it is required to revise the section of our beam. That is very important, because just checking this condition is not sufficient. So second condition is if our tau c is less than tau v is less than Proxy Max, means tau v value is greater than tau c, that in our case it is applicable, and tau v value is less than Proxy Max, that also applicable, means our case is the second case. Second condition will apply in our case. So which means we have to calculate the shear reinforcement without revise the size of our beam. But if this condition is not applicable, suppose, means what happen, your tau v value is greater than tau c as well as Proxy Max too. So in that case what you have to do, you have to revise the section value, means you have to revise the width and depth of the beam, but this is not required for our case. So let's calculate the shear reinforcement required for beam. So first of all we have to calculate how much shear can be handled by this concrete and this section. Okay, so for that we have a formula, shear registered by concrete VC will be equal to tau c multiplied by B into D. So we have all this value, just put down, so you will get the shear registered by concrete value, and that is 68,400 Newton. Now let's calculate how much shear, for how much shear we have to design the shear reinforcement. So for that we have to deduct the concrete registered value from the overall value. Overall means whatever the shear force we calculated earlier. So just 71832 minus of 68400, so we get the value that is 3432 Newton. Means for this much shear we have to calculate the shear reinforcement, means this much shear will be registered by the steel and this much is registered by the concrete. So for that let's consider the 6 mm dia stirrup which is 2 leg, and based upon that we calculate the spacing of the shear reinforcement. For that this is the formula, VUS will be equal to 0.87 Fy into ASV multiplied by D divided by SV. So here note down, here Fy value is the characteristic strength of the stirrups, not the main reinforcement which is given in the problem, not this. Okay, so 6 mm dia stirrup which came in a mild steel form, so we taken Fy value as a 250 Newton per mm square. Please note down this. And ASV is the area of the stirrups. So here we didn't calculate the ASV earlier, so let's first calculate the ASV so we can further move on in this formula. So ASV will be equal to 2 times pi by 4 multiplied by 6 square, means the area of our stirrups. As we use the 2 leg stirrups, so 2 multiplied by area of the bar, that is pi by 4 6 square, which is coming out as 56.55 mm square. So just put down all these values and you will get the spacing, required spacing for the stirrups. So required spacing coming out is 1434 mm, means its meaning is we can provide the 2 leg stirrup of 6 mm dia at 1434 mm spacing, but IS code doesn't permit this much spacing. Okay, so we have to cross verify the spacing with the IS code criteria, and based upon that we decide whatever the final spacing we can provide in our actual beam. So what is the criteria? So as per the IS 456, maximum spacing for stirrups that we permitted is 0.75 of D, that is 0.75 of effective depth 400 mm, which coming out as 300 mm, and second condition is exactly 300 mm. So which means our spacing do not greater than of both of this value. Okay, so just verify this thing, but in our case our required spacing is more than both of this value, so we have to consider maximum spacing is a 300 mm. So based upon this we conclude that we require the shear reinforcement as a 2 leg 6 mm dia about 300 mm center to center throughout the beam section. Okay, so this way we can calculate the shear reinforcement for our beam. Okay, so next step is to check for the deflection. Okay, so we calculate the shear reinforcement, we calculate the main reinforcement, but we have to check whether our beam is safe in a deflection or not, because if it is not safe in deflection, then we have to revise the section in that case also. So let's check for the deflection. So for that we have to require some parameters, like first is basic L by D ratio. Okay, so basic L by D ratio also vary depending on the type of the beam. So if you read the IS 456, you will get this table. In that they are specified for simply supported beam, its value we have to take on as 20. For cantilever beam, that's value coming out 7, and for continuous beam the value of L by D basic is 26. So as our beam is simply supported, so we taken as a basic L by D value 20. Correct. So next parameter we have to calculate Fs. Fs formula also given in the IS code, that is 0.58 times Fy multiplied by AST provided upon AST required. So Fy is our main steel grade, that is 415. AST provided means we provided three numbers of bar of 20 mm dia, so whose area is 942 mm square, and whatever the area coming out based upon our moment, design moment, that we consider as a AST required value. So based upon that, Fs value comes out 246 Newton per mm square. So now you people thinking why we calculate the Fs value, because based upon Fs value we have to calculate one parameter which is called the F1. So if you find out one figure in IS 456, you can see easily here bottom FS formula is given. So this is a different chart, okay, for depending upon the FS value and the modification factor we have to calculate. So we required FS value and percentage of tension reinforcement. As we already calculated percentage of reinforcement 0.785 and FS already we calculate here. So based upon that, our modification factor value coming out as 1.1. Just you have to read this graph carefully so you easily get the value of F1. Value of F2 is for the compression beam. Means if you design your beam as a doubly reinforced beam, in that criteria this value comes into the picture. So our beam is singly reinforced, so just be taken as a 1 value, okay. And next F3 value. F3 value is for used for the flange beam. Flange beam means if your beam is L type or T type, in that case this value comes into the picture. But in our case we design the rectangular beam, so we do not require this value, so just we simply taken as 1. So based upon that we calculate the maximum L by D ratio, that is basic L by D multiplied by F1, F2, F3. This is the formula, so which coming out as 22. So maximum this much ratio we can provide for our rectangular beam. So let's see how much we provided. So based upon that we can decide whether it is safe for deflection or not. So whatever we provided, whose value is 6230 divided by 400, that coming out as 15.58. okay. So whatever the L by D ratio we provided, which is less than the maximum permitted, that is 22. So which means our beam is safe in a deflection, so we do not have to worry about the deflection criteria in here. So this way we can design the rectangular beam as per the IS 456 codal provision. So hope you guys understand the process of the rectangular beam design, okay. So now let's see the detailing part. That's the last portion of this design. Whatever we calculated, so this is our beam, this is our width of support, so this is our bottom reinforcement that we calculated 3 bars of 20 mm dia. This is our stirrups, that means shear reinforcement, 6 mm dia, 2 leg, about 300 mm center to center spacing, and this is our top reinforcement, okay. So top reinforcement means the minimum reinforcement just we have to provide. So we selected as 2 dia of the 12 mm, okay. So you have to calculate the minimum reinforcement, based upon you can get this value easily. So this is our longitudinal section and this is our cross section, okay. So this way we can design the rectangular beam as per IS 456. So hope you guys understand the design procedure and all that things, and if you really like, please like the button of this video. Also comment me if you really want more video like this, so I will make for you guys surely. So just if you come here for first time, subscribe our channel also and press the bell button for future notification. Thank you so much for watching this video.